All right, everybody, let's commence. Welcome you all here to another one of our space talks. Tonight we have a guest from JPL, from NASA in Pasadena in California. Bob Shishko is going to talk to us tonight about some work that we've been doing. Serkan Salem has been on his sabbatical. He spent a few weeks over there, and he has a student working here who is here, Carlos, has been working on the project with them on which you'll hear all about. I don't need to talk about it. Okay, so let's introduce Bob. He's a principal systems engineer and economist in the Project Systems Engineering and Formulation section at JPL. He teaches space systems engineering, logistics and economics at ISRU in Strasbourg. He's worked on operations and logistics issues for NASA, major human space flight projects over the last 30 years, including the Space Station Freedom, the International Space Station, Constellation, as well as JPL robotics missions to Mars and Jupiter. He's one of the founding fathers of the Project Design Center at JPL, and as a principal contributor to and task manager for the NASA Systems Engineering Handbook. He was awarded the NASA Exceptional Achievement Award in 2012. He served as the Chief Engineer, Infrared Space Systems Director at US Air Force Space and Missile Systems Center. He's an adjunct professor at the University of Southern California and has authored portions of 6 books and numerous technical papers. Could you welcome Bob, and we hope we enjoy the presentation. Thanks, Bob.
Well, thank you. Can you hear me?
Yes.
Okay, and welcome to you too. Now this talk is really an initial progress report on some work, as Andrew mentioned, that we have been doing as a collaborative effort among several partners for NASA's Office of Emerging Space. The Office of Emerging Space has the goal of essentially to help grow the future space economy. We see commercial companies taking over functions that were previously done by the government, things like delivering supplies to the International Space Station. And these kinds of commercial activities are, including off-Earth mining, are going to naturally grow as we expand human presence in the solar system. So the team consists of mostly myself, but there's a lot of other people at JPL who are interested in the idea of expanding human presence into other extraterrestrial locations, so becoming a multi-planet species. So I'm getting a lot of help from people who have a natural interest in this task. And then here from UNSW, I have Professor Salem and Carlos over here, and Professor Andrew here, and Jeff Colton from the business school aspect. So this talk really has aspects of mining, of economics, of system architecting and engineering. We're bringing all that together, as we will need to do. Also part of the team is a small group at MIT as part of their interplanetary supply chain management and space logistics program, which is kind of a very unique program. Professor Devek and a graduate student, Sydney Doe. Sydney is actually from Sydney. He went to that other school, apparently, for his undergraduate work, but now he's a PhD student at MIT and soon to get his degree. Sydney delivered a paper at the International Astronautical Conference in Toronto last year, And that paper received an avalanche of media attention because it essentially debunked the Mars 1 plan to colonize Mars in 2023. Mars 1 is a corporation a non-profit supposedly corporation in Holland, and they mostly sell people on the dream of going one way to Mars. Unfortunately, Sydney's paper said that they would die basically within 100 days of going there. So that received quite a bit of media attention. Sydney is also a contributor to this task. So most of NASA's effort right now in human spaceflight is focused on what I would call the first of 3 giant steps, that of getting the first humans to land on Mars. Okay? There's a lot of efforts, teams that are formed that are trying to plan various and analyze various ways of doing this. The second giant leap is establishing a colony on Mars, in which people basically will go there and stay there permanently. That's kind of pretty far in the future. But our research is beyond that, to a sort of unknown time frame, far into the future, when Mars colony achieves, in some sense, economic viability. So, that's kind of the scope of this research, and represents kind of the third of a series of giant leaps. So, our immediate research objective, and that's what we promised the Office of Emerging Space, is to build and integrate 4 models in order to have the capability to perform what's called an analysis of alternatives, an AOA. So this progress report will focus, for the most part, largely on the first model, but we'll talk about the other models a little bit as well. So the Mars Colony Architecture Model, or MCAM as I call it, is actually a semantically aware data repository. Think of it as the mission control room or mission control center for doing the analysis of alternatives. The extraction process model, and by the way, these logos indicate responsibility for each of the individual models. JPL is responsible also for integrating them. The extraction process model here, you can think of that as the mining model. Okay, focuses on the technologies of in situ resource extraction, processing, and delivery. So this is where the mining aspects come in. And by the way, when we talk about mining, it's not just mining for minerals, we're also talking largely about mining for water on Mars, even mining for oxygen out of the Martian atmosphere, which is largely carbon dioxide. So mining has is meant in a broad sense here. So this is another model in this is called HabNet. Now this is HabNet basically simulates the fundamental sustainability relationships associated with establishing and maintaining a Mars colony of population X. Okay, so HabNet is actually a fairly high fidelity simulation of all of the functions that that ensure the survival of the individual colonists. So it deals with essentially the environmental control and life support systems, things like the water processing facility, the urine processing facility, we convert urine into drinkable water, the carbon dioxide removal, and so on, things that maintain the habitat and the condition in which humans can live. It also includes things like growing food. If you've seen the movie The Martian, this may be kind of a reference point for you. And lastly, the economics model brings together information about the mining investment and operations costs as functions of time, with the objective here of determining the profitability in a commercial setting. So what we've shown here with the data flow is some of the information that's passed from one model to another. So the MCAM essentially provides technical parameters to the mining model. It also provides the idea of the number of colonists to be supported, the activities and physiological requirements of the group of colonists. The habitat or HabNet basically then computes the amount of net water demand. We are focusing on water in this discussion. So the net water demand is passed to the mining model. In other words, how much do we have to extract from local Mars resources in order to support the colony? And that extraction process model basically tells us the equipment that we need, and the numbers involved in each type of equipment, and the total water delivered over time. And all that's fed into the economics model along with technical parameters, things like that space people talk about: mass, volume, power, but also things like the development cost and unit production cost of those items of equipment, design life, some economic variables such as the water, the initial price of water on Mars, delivered to the colony on Mars, or delivered at the location of the colony on Mars. Plus things like we do in business schools, like when we track commodity prices, we have parameters that we call price drift and volatility, and things like taxes, tax rates, and so on. So we are able to kind of turn a lot of policy levers and technology levers here to see what kind of combinations will provide an economic viability to a commercial enterprise investing in extraction processes. So beyond our immediate objective of building and integrating these models and kind of using them in a way to investigate kind of all the alternatives, beyond that immediate objective is a broader aim to dig deeper and more formally into what form a Mars colony might take and what operations might be like in such a colony. We want to do this through the application of a formal architecture definition process. In other words, we want to establish the idea that to be serious about a Mars colony, we need to apply formal system architecting methods and tools. And that's something that has been recognized in the International Standard for System Engineering. That's ISO 15288 in its latest version. So system architecting is kind of a high-level process that establishes the basic artifacts and relationships, okay, across a system. So we could have chosen a number of approaches to doing this system architecting to describe the Mars colony or Mars colony architecture. We chose one based on the Department of Defense Architecture Framework, or DODAF. It's very similar also to the Ministry of Defense Architecture Framework that's used both in the United Kingdom as well as Australia. We chose the DODAF, latest version, 2.02, with some for-purpose extensions. Now the reason we chose that, we have basically three reasons we chose that. First of all, DODAF, MODAF are high-level representations of system or system of systems. So the constituents of these system of systems are themselves very complex systems. Okay, but we don't want to deal at that level. We want to deal kind of at a higher level where we can talk about a rover or a processing facility as entities in themselves without going into further detail about them, unnecessary design detail, if you will, but just the technical parameters that enable us to do kind of analysis of alternatives. Second reason is that DODAF and MODAF have a more of an ops focus than some other methods used in system architecting and system engineering. So we don't want to focus on requirements or design or verification and validation. We want to focus on how things will work together, if you will. What are the interfaces between these systems that must function within a very complex system of systems? And the third reason is that there have been recent changes in DODAF. These changes allow for more than just photons to be exchanged between operational locations. When I say photons, I mean information, messages, those kinds of things. Now, people and resources can be exchanged among these operating locations. So that came as something that is absolutely necessary to describe a Mars colony architecture. Nonetheless, we still needed to have some extensions of DODAF and to overcome some of the limitations in supporting analyses. And one of the extensions we needed to make is to bring human physiology into the picture. And I'll talk a little bit more about that as we go into it. So MCAM is actually a relational data model, and it consists of essentially multiple interrelated data tables, and those tables have a lot of information in them. So let me explain some of the fundamental building blocks of the MCAM, the Mars Colony Architecture Model. And these are things that are somewhat extensions of the way DODAF their constructs in DODAF. So the first construct is the notion of an operational node. And in our space logistics work, operational nodes are basically surface locations on the Earth, on Mars, on the Moon, on Phobos, essentially. Any place within the Moon, Mars, Earth system. But operational nodes can also be orbits. There are specialized orbits that we are looking at in NASA as maybe waypoints or as a transfer of material. These are trajectories that take you to Mars and back. So orbits are also operational nodes, not so in DODAF. So this is obviously an extension we need to deal with space. And lastly, operational nodes can be Lagrange points. Lagrange points are special points in which essentially the gravity forces are in a form of equilibrium. So next, systems. So we have, and this is again similar to what's in DODAF, but here we can have transport systems, we can have mining systems, we can have habitation systems. Any of these artifacts can join essentially into this database. Operational activities and functions. These are things like mission control, training of astronauts, but it also includes things like mining in our MCAM. Resources. Resources can now, as I mentioned, are more than just information. They can be people, it can be material. And all we need to do is identify them. Now, milestones is something new that doesn't exist in DODAF, but is absolutely essential in our modeling of Mars colony architecture. Milestone is not just a date, it's a location. So it's actually, think of it as kind of four-dimensional space-time. It's not only when something happens, it's where it happens in the Earth, Moon, Mars system and within the architecture. We also have things like need lines and operational flows and system flows. These are things I'll show you a little bit later. Measures is essentially any property that you want to be able to identify and provide a quantitative value for. So things like space system engineers are very concerned with mass. Logistics people are concerned with capacities. Reliability engineers are concerned with reliability. So all these things represent measures that we want to be able to quantify at some point within our analyses. We also have introduced the notion of a performer. Now, a performer in MCAM can be either an organization, such as a space agency. You can assign, therefore, responsibility for a function or for a system to a space agency. It can also be an organization. It can be a system. A system can be a performer, particularly if it's automated. Or an individual or team of individuals, people, can also be a performer. And that plays an important role in determining who's going to do what in the Mars colony. And lastly, there are a set of rules or standards, so engineering standards. For example, a standard that we would use for communication, like the CCSDS standard. So this is also a construct within MCAM that allows you to assign such standards to the interfaces between two systems, for example. So, as I said, we had to extend DODAF, MODAF to some extent to permit what we want to do. But what we want to do, of course, is quantitative analyses. And for that, we need quantitative relationships. So for ISRU, In Situ Resource Utilization, okay, we need mining, if you will. We need to know something about the extraction rate based on particular technology. How many mining systems need to be deployed to deliver or fill a certain demand for that resource. The number of people that are needed to operate that kind of mining technology. And that, of course, determined by how much automation there might be. So these are the kinds of quantitative relationships we need in order to do our calculations. Fancy picture. Okay. So, let me reiterate, MCAM's purpose is to support an exploratory investigation of various Mars colony architectures, concept of operations, and representative scenarios. And, okay. MCAM has a certain set of uses within an architectural definition process. So what an architectural definition process must do is to address stakeholder concerns. So you identify stakeholders and they identify concerns. This gives rise to conceptual architectures, which include the artifacts I just mentioned, and the relationships. And those get formalized in the database, in the MCAM. The MCAM then provides that data and other info to a set of models and simulations. Those are the extraction model, the economics model, the HabNet, and so on. And those models and simulations do their thing, make their calculations. That enables various analyses, and those are being expressed in what's called views within the architectural definition process. And those views, and we're going to be showing some examples of what I mean here, those need to address the concerns. And those views must also communicate understanding to the stakeholders. Okay. So let me give an example. As a colonist, okay, I'm a stakeholder, as a Mars colonist, I am rightly concerned about my survival on Mars. So it is incumbent upon the system architect to show through detailed analyses how each proposed conceptual architecture would or would not lead to a favorable outcome concerning my survival. And so, yeah, we have to then say, well, here are the systems that are going to support your environment and your life. We're going to do analyses which, say with HabNet, that show that, yeah, you're not going to die of oxygen, overabundance of oxygen or an underabundance of oxygen. And we've done this analysis and we can show you, and that should address your concern. So this is apparently something that Mars 1 did not do, is to provide the analyses and to the colonists that they in fact would survive a reasonable amount of time. Instead, what they did is they sold T-shirts to such people. So you've got a little sarcasm here, but there's good reason for that. Okay. All right. So let me give you a context diagram. This is kind of useful to get your thinking kind of in line with what I'm going to show you. So the Mars colony is actually a very, very complex system of systems by itself. But in fact, it is a part of an even larger system of systems. And that larger system of systems consists of what we call the interplanetary supply chain, which in itself has its own large systems in it. And then things that people forget about, the terrestrial enablers. And when I put together this diagram, you know, it's the things that the engineers are focusing are all up here. You know, all the space engineers and so on, and mining engineers as they focus on this. But all these people that we have in NASA and other space agencies, they're all focusing on things like this. In fact, when you look at this, we have a lot of these things already in some form. And perhaps the only thing that we're missing here is kind of a benign legal regime and treaties that basically define what you can and cannot do on Mars. Okay? But the other things that, you know, we have various infrastructures, industrial bases, markets. Those are things that we already have that will enable us to go forward and, you know, kind of build, you know, this, build a colony on Mars and perhaps elsewhere. So, so I wanted you to have this picture in mind, and I want this is the mental image that I want you to take away from this evening's talk here. So to realize how complex this problem is. So now what I'm going to do is show you the individual tables that make up what we're calling the MCAM. So the representation of MCAM is as I said, is a set of data tables, and this is called an entity relationship diagram for that database. It's actually too big to fit on one slide. I actually had to put it on 3 slides to show you. But I just want to give you an idea of some of the things that are on it here. So, for example, here is just the list of the operational locations. We're calling those nodes within the Earth, Mars, Moon system. So it's just a list here. So here's another list of resources that we're concerned with, like oxygen, water, minerals, food, things that humans might be interested in. And in fact, this part down here is just a list of systems that comprise this mega system of systems. So there's more. Okay, so these are more tables. So here we have things called measures. This is just a list of properties of interest, things like mass, cost, and so on. Here we have, this is a more complex table since it now is a merge of several of the individual tables, but this is where we capture, right here, there we go. This is where we capture the attributes of all the systems we are talking about. Okay, right here. And we capture the attribute values at a point in space-time, okay, at a milestone. Okay, now here we focus on the human activities. And so what we have here is a list of what we call person types, but in fact, person types are defined by skills. And in MCAM, I've actually used the U.S. Bureau of Labor Statistics has what they call standard occupational classifications that they use. And rather than invent anything new, I just use that because eventually, in a Mars colony, you're going to see all the occupations that you're going to see on Earth are going to be on Mars. So no use inventing anything new here when we've already got something that's good. Now this table here is another one of these composite tables. And this is where we capture the attributes of colonists at a point in space-time. Now, you know, it's not just the number of colonists of concern, but we actually want to track the number of colonists by skill, that is, person type, and by gender. Well, you know, there's a couple of reasons for that. Basically, you want to have approximately the same number of men as women, and vice versa. That's just what makes being a Mars colonist interesting. But also, there's a more practical reason, okay? Because males and females have different physiological requirements, even when performing the same activities. They consume fewer calories, which is very important when you have to grow your own food. So things like that, and of course DODAF has nothing like that even, but we needed to introduce these extra tables into the MCAM in order to do the analyses that need to be done on, for example, how much food needs to be grown. Okay. So this is what the database looks like, and all the quantitative values that we've captured here are used by these downstream models to do more complex analyses. So we can do some basic kind of DODAF views with the information in our tables. These are, you know, some of the, you know, rather standard views that are produced in defining a military system or system of systems. But we, as I said, want to generate some more complex views, such as the commercial profitability view. And that's going to take a little more effort. So let me show you how this all works, okay? So what I'm doing is I'm providing an example, a simple example, of how all these tables will work together to produce something about the profitability of mining on Mars. So I mentioned we have operational nodes. Well, here's my table that defines all the available operational nodes I can think of. And I've actually got something on the order of almost 50 now. These are locations on Earth, Moon, Mars. I've got orbits, I've got Lagrange points. And some of these represent fairly familiar things to you, like a launch site at the Kennedy Space Center. But what I've done is I've highlighted here, for my simple example, I've highlighted 3 different nodes. A Mars settlement, a Mars water mining site, and a communications relay orbit around Mars. This would generally be an aerostationary orbit over the Mars colony. Aerostationary means it's like geostationary on Earth. Okay? So I'm just taking my simple example with these 3 operational nodes. And there they are. I'm going to just draw them out as very simple. Now, these operational nodes are going to have what we call need lines between them. These are things they're going to need. So, for example, the Mars settlement here, Mars colony, if you will, what do they need from the water mining site? Well, they mostly need water, okay? But they're also going to want to have some telemetry, okay, to tell them what's going on with their machines, if you will, that are operating at the water mining site. Now, the water mining site, those machines are going to need maintenance services from time to time, and that's going to come from the Mars colony. And they're also going to want commands. You know, should I stop? Should I turn left? So they need to have commanding, essentially. Now, both the Mars colony as well as the water mining site are going to want what we call PNT, positioning, navigation, and timing. These are what you get actually from GPS satellites. That's how you know where you are. So you're going to need that from orbit on a sort of regular basis. So these are what we call need lines, and in MODAF, this is called an OV2 diagram, just showing the very simplest things that are essentially interface needs between the various operational nodes. Simple so far. All right, so let me just give them a number. I've used up 1 and 2 already in my database, so I'm going to give them numbers 3, 4, 5, and 6. These are capturing the need lines. The way you translate this now is in a database, and this is what the database looks like. This is the need lines table, and you can see I've identified the need line by its number, and I've said, give it a name, and I've given kind of what it is. But the most important, I've identified for each of the need lines what the sink and source node is. Okay? That's all I'm saying. Like, what is the sink? What is the source? Later on, I'll tell you what goes into these individual need lines. So, simple enough so far. So now let me introduce resources. And I've listed a bunch of resources here. I've given special attention to information and to human labor as being 0 and 1 here. But water is pretty important, so is oxygen. I certainly want a certain amount of electrical energy. And then I'm concerned with food, perhaps nitrogen, methane. So these are just my list of resources. And all I'm doing here is identifying the resource and saying how I'm going to measure it. Okay, what units are used. All right. I'm also going to introduce some systems now. And I have a list, and by the way, this is only a partial list of the systems we have in the NCAM. There's over 100 now. And there are all kinds of systems. These are launch vehicles. These are systems that are what we call habitats. They're surface mobility on Mars. They're power systems, and in this case, essentially fission nuclear reactor. And I've identified, as you can see, I've highlighted 7 of these systems within this long list, and you know, unlimited list that you can make of potential systems of interest. So I've identified 7 of them, and in particular, I want you to focus on this one here, the Mars In Situ Water Extractor, because that's going to be an ISRU system. And kind of a picture of it. It's a rover. It has a drill and an auger, and it extracts regolith. It then using advanced Stirling ASRGs, advanced Stirling, some
radioisotope generator.
Radioactive generator, yeah. To convert the regolith by heat, and get the water out essentially, and store it. So this is one of the systems that I'm going to be looking at in the trade space. So we also have a Mars In Situ water transporter, and we also have a kind of a power plant that's a part of this particular architecture. So I've got these. Now, what I'm going to do is I'm placing these systems within my operational nodes. So this tells me that, I've got a power system here, the one I've identified. I've actually got an oxygen extractor from the atmosphere. I've got a greenhouse, I've got a habitat, and at my water mining site, basically I've got a MISWI and a MIS-T. And I've got a positioning satellite or satellites in Mars orbit. So now I've placed systems within the operational nodes. Now, let's look at what is being exchanged between the various systems. So obviously the power system is supplying electric power to the habitat, to the oxygen ISRU system, to the greenhouse. And here we have things like maintenance services are being provided by the habitat which the colonists live, providing maintenance services to both of these types of systems. Obviously water is being provided back. So here we have essentially the system resource flows. Okay, and this is what in NODAF is called an SV6 diagram. And what you can see here is that there's actually 22 interfaces that we need to keep track of to make sure, for example, that the power system is sized large enough to handle the power demands, or this whole MISWI transporter and water processing plant is sized to support the Mars colonists. You need to be able to answer those kinds of questions. So we do that. We've identified our 22 system resource flows, and this is the table version. This is how we convert that diagram into a table, and this is essentially the SV6 table. And it contains a lot of information here. So for example, it says for each flow you identify the resource, you identify the sink and source system, and if you'll notice, atmosphere you get for free on Mars. We also identify what I call the flow periodicity, whether it's continuous, whether it's irregular, whether it's periodic, which means it occurs at a certain pace per unit time, or whether it's irregular, like unscheduled maintenance on a system. So you identify the flow periodicity, you identify the flow means. For example, power is transferred from one system to another by, guess what? A power cable. Now, you may want to also specify that it's a certain size or meets a certain, essentially, a standard of some sort. Now this table goes on. There's more, there's more columns over here. So I had to put them on another page, though. But now it also tells you, for example, the performer, and you can see in most cases a system is the performer. Sometimes a person is a performer, but whatever performer the architecture includes, you have to identify it. So you identify which system is responsible, for example, for providing the power cable. Okay, and if it's a person, you have to specify the person type. What skill is needed to do, for example, maintenance on the MISWI. You also specify, very important, the flow rate. The flow rate, and of course the units, but the flow rate this is where you can essentially ascertain whether you have enough power, because now you can add up all the power demands, okay, within a given mode, all the power demands from your systems to see whether the power system can supply that amount. So you can do your sizing or your margins, if you will, for power margins. Margins are very important in space system engineering. So this table captures all that kinds of information. Now from this, we can actually now build. We can actually build our need lines table by resource. So remember we had need lines 3, 4, 5, and 6. Well, now what I've done is broken this down to say that need line 3 consists of it consists of these 3 flows, system flows that we've just identified. So obviously, from the water mining site to the Mars colony site, we said water was important. But you'll notice that there are 2 kinds of information, or 2 flavors of information here that must flow also. And this allows you to capture that. So what is a need line? A need line is a bundle of system resource flows. Okay, and this table will tell you what makes up that bundle. So why are there different flavors of information here? Well, for example, the bandwidth might be different between the 2 types of information or flavors. The refresh rate, in other words, the update frequency. So the MISB might want to know its location every 30 seconds, whereas the transporter might require an update every 5 seconds. So the refresh rate on the information might be very different. So you have different flavors of information, and you can capture that in this table. There also might be different flavors of labor. You might need a highly skilled maintenance person, mechanic, or a lesser skilled one, depending upon what the need is. So you're able to capture that. And this is in DODAF, it's called an OV3 table. Okay. So again, it gives you the idea of how MCAM, what kind of information is in MCAM. Now we get to the stuff that's probably more interesting to the miners here. We'll move on now from the MCAM to the extraction process model. And this model was built by Carlos for the idea of the MISWI and the transporters and the processing plants. And what he's done is he's now taken his inputs, which come from MCAM, things like the drill rate and so on, and now he's computed, given a demand, a net demand for water at the colony, he's now computed the number of machines of each type through an optimization algorithm. Now that information then gets passed on to the economics model. The infrastructure model or HabNet model basically provides essentially the demands for power, for the habitation, ECLS, environmental control and life support systems as the colony grows. So it provides essentially the internal demands for in situ resources like water and so on, the net demand that must be met by the extraction process systems. It also deals with, we need to deal with the spares to support the colony and its IRSU system. And we can also have additive manufacturing built in. Additive manufacturing is like 3D printing. Okay. So that would ameliorate the demand for spares if you could just print your own spares on the spot, using perhaps regolith as an input, Mars regolith as an input to the 3D printer. So we haven't got that all built into HabNet. It's limited right now to providing the water demand. But eventually, the infrastructure and ILS model will have to provide answers to these kinds of questions. So in general, this model will provide what the Mars colony and what the interplanetary supply chain look like over time. Okay, and lastly is the economics integration model, and you can sort of see on this side kind of the types of inputs that are needed. And this model's idea is to address, really to answer questions like what markets are likely to materialize, what technologies are likely to be available, and what production efficiencies would be needed. And ultimately, the model does compute things like net present value, return on investment, option value, real option valuation, and other important parameters for the commercial aspect, such as what's the probability that the net present value will exceed 0 in some scenarios. Now what's built into this model is a Monte Carlo capability in which we have a stochastic process that generates essentially prices over a 20-year period. So that's kind of a forecast, and that's based on standard commodity models with drift and volatility in the prices. This is what we see all the time in the mining world. Prices for commodities can rapidly change over a long period of time and have this sort of random process that generates them, that propagates them through time. And in fact, what you're seeing is a graph of a simple geometric Brownian motion generating essentially the price index for water on Mars. So that all gets, that all is incorporated in the economics model, and we are able to address the kinds of concerns that entrepreneurs, space entrepreneurs have. Okay. Okay, so last slide, summary. A Mars colony architecture is going to be driven by just 5 things: orbital mechanics, human physiology, what technologies are available for our systems in the future, the Mars environment, for example, how much water is in the regolith at various locations. We only have very coarse knowledge about that. We need to have almost down to meter level estimates for the amount of water for a Mars colony to be, to be survivable. In fact, I think it's today or tomorrow. Well, it's today. It's Tuesday in Houston, Texas. There is a workshop with people from, I guess, all over the world. They are right now figuring out what should be the first site, the first human landing site on Mars at this very moment. So and what do they have to consider? They have to consider where we can live, where the resources are, and there's big trade-offs. The water, for example, at the poles is easily extracted, but it's a long way away from where you might want to establish a colony for purposes of solar power generation. So there's big trend, and then the other aspect is where's the interesting science? What are you going to explore? So there are huge trade-offs in that, but right now people are looking at precisely those questions for the first time. So, and lastly, economic and social constraints are going to play a role as well in describing what an architecture would look like. So MCAM and the other models, their purpose is to support, again, an exploratory investigation of various architectures, which includes the landing site, concept of operations, and representative scenarios. It houses the architectural information in a structured way that enables standard views to be constructed, but when integrated with some sophisticated downstream models, will enable more complex views to be developed, in particular those that might be interesting to the mining community. That's it. So I think one of the ideas here is that students need to have they need to be cross-trained in a lot of disciplines. If you're going to be a mining engineer and you want to do it in space, you're going to have to know something about these other things here. So that's, I think that's the way it ought to be. We got to get smart by knowing more than just our limited discipline. Okay? Any questions?
Is the early market that you considered on the Earth, have you thought about what might happen with I don't know, like a breakaway market on Mars? They get a bit cocky, start selling stuff to themselves?
Well, I know the market that seems to be developing is for asteroids, because they can, but there's still the same problems. They need to be able to characterize an asteroid and then be able to get there, do the extraction, and then somehow return it to a useful purpose on Earth. But that seems to be the way the space economy for mining is growing. But remember, the big, NASA is focused right now on Mars. It's not focused on the moon. But the next administration may pivot towards the moon. And resource extraction on the moon, again, is within our current technology. The idea is there. You extract the water from permanently shadowed craters, gets converted into propellant, and placed in orbit around the moon in a propellant depot, and that humans use that to go to Mars. So there have been studies that have at least talked about this, not much quantitative analysis of late. So the market may develop on the moon first. We don't know. It's one of those uncertainties. But it very much depends on the political winds and where NASA and its traditional partners want to put their efforts.
But don't you think that its operation could be more difficult, establishing operation more difficult on the moon compared to Mars because of the environment?
Well, it's a good question. We can certainly do analyses and we know pretty much, how much we can deliver with various size systems. The question again is the ground truth. We know that, or we believe from orbital observations that the moon may have a lot of water, again, hidden in various forms within these shadowed craters, but we don't know the absolute ground truth. We don't know exactly where, and we really do need to essentially send missions, robotic missions, to find out that ground truth. So we don't know the answer. That's why you want to do it in modeling. It's cheap. And look at various assumptions and then see how the science, does the science bear out the assumptions? And if not, what assumptions then are scientifically reasonable?
To me, it seems like you're going about this as if a capitalistic approach is the only way to do it. And to me, it seems like lots of these costs are just huge,
Right.
and that maybe there's different economic strategies to this.
Well, it's a good question. One of the things that we'd like to know is how long will a Mars colony require subsidies from Earth? Because the price of water on Mars is going to be very high. But that's a way. That's another question. That's another concern that a stakeholder, i.e., taxpayers, are going to want to know. How long are we going to have to subsidize a Mars colony until they can stand on without such subsidies? And subsidies could be in the form of having essentially no tax on income, on corporate income for those resources extracted on Mars. So various policy levers. There's direct subsidies, there's tax policy, and that's a good question. When can the subsidies stop?
Sorry, when you talk about no tax, who would the tax be paid to theoretically?
Well, if you're a mining company, the mining companies pay taxes to governments. I imagine a variety. International companies pay a variety of taxes to a variety of countries.
They have to bring the dollars to Earth, right?
Yeah. Well, the dollar's already on Earth.
So wherever the company's head office.
It's a tax item on the moon.
Is this a tax class? Are we talking about? This is
They got an assignment tomorrow for cost.
architecture class.
Not a tax question. Are there any active discussions regarding sending out waste of some sort, like CO2 or radioactive waste? I know there has been discussions regarding that to send to space, but are we going to send waste now to Mars, or any discussion on that?
I don't think, it's very expensive to get to Mars.
Okay.
And it's more expensive
So
to
it's
come
not-
back.
Okay.
But,
You're sending human.
Yeah, I don't think we'll be sending waste to Mars.
Okay.
Okay.
Is there any competition between the country to pioneer the Mars first, or any competition? Or
Well,
Any danger?
The NASA, the official NASA position is that we want to do this on an international participation basis. And I doubt that will not change. Right? That's in a presidential space policy that we encourage international participation. Okay.
Just a question. So one of these systems sort of rely quite heavily on technologies. What do you see as being one of the sort of key technologies that requires the most of the improvement, or the biggest sort of, I suppose, changes in status quo to sort of be executed in a successful manner?
Well, we're just getting started. We're waiting for the mining people to give us a conceptual system that we can put into this and then run it through end to end. So we're waiting for the engineers to come up with ideas, starting on a cocktail napkin and then, sort of developing to sufficient detail that we can do an analysis. But that's, we don't have an answer yet. We're building this so that when a new idea is put forth, we can do the analysis and investigate the entire trade space.
Does any other space agencies have shown interest on this particular topic? So most of the time I find NASA is talking, but on establishing economy on colony Mars. But what about other space agencies like ESA or ISRU or
Yeah,
JPL?
so this is a good, this is a topic all its own. And our traditional partners, ESA, JAXA, even the Russian space agent, have shown an interest more in going back to the moon rather than going to Mars. Whereas NASA is focused on, you almost can't talk about the moon. So, as I said, whether future administrations will pivot more towards the partners. In fact, the head of ESA is talking about a moon village. This would also require analyses of ISRU potential. And so if I did this whole lecture and just replaced Mars with lunar, everything would still be valid.
Let's say that a mission to Mars is successful and some huge discovery is, let's say the center of Mars is full of gold. Who would take ownership of that?
Well, that was the issue I brought up earlier. There's no legal regimes or treaties that says what you can do on Mars or you know, who owns what, or can you extract the resources. Presumably, if it's an international venture to go to Mars and establish a Mars colony, that the logical thing is that we extract those resources for the benefit of the Mars colonists. So, yeah, there is a problem that there's no ownership in any treaties or legal regimes that would protect commercial or not protect commercial.
It was a collaborative effort between multiple countries and presumably internationally several government jurisdictions contributed different funds and different resources and intellectual property and all those sorts of contributions, whether it be tangible or through goodwill. You need to sort of split it fairly equitably.
Yeah, I mean, the resources would be extracted for the good and welfare of the entire human civilization.
I'd like to see that happen.
Yeah, but you know, that's again. Did I go into the law school? Okay.
All right, maybe two more questions.
Okay.
Yes, I can see another driver, obviously, for getting to Mars is the search for life. And I can also see that the other driver, being mining, might be in conflict with the search for life. Is there any provision in your model to take this into consideration?
Well, there's a couple of ways to come at that. The answer is there's no provision for it, but since scientists are a stakeholder, a very important stakeholder, that they want, and now we have a lot of requirements to not only protect humans on Mars, but also to protect Mars from humans. So there's a lot of NASA and international requirements, or requirements imposed by individual space agencies that they not contaminate Mars. But this is part of choosing the landing, the site of the first human landing. It has to be scientifically interesting, perhaps support ISRU, and part of that make science endeavors feasible as well. So yeah, that would have to be taken in, and that's kind of what comes under what I call social constraints here. You know, that you're not disturbed. And there is an effort underway, as with the next Mars mission, is to see if when we go to the sites that we believe have had water at one time, or may have water within the first couple of meters, whether there's life there. We'll be able to ascertain that long before we send humans. So we'll have some knowledge about that, about where life might be on Mars. But again, it's a trade-off that has to be discussed with all the stakeholders. Those are a good example of a concern.
How do you future-proof the Mars program against the apathy of American citizens? Because we know that's what ultimately killed the last mission to the moon. What happens if in 10 or 20 years after you've built the colony, Congress says, no, our priorities are health rather than Mars?
Well, I think once you have people up there on Mars, So here is the idea of the, some of the, if I name sort of the large group of stakeholders here, and what their major concerns are. Space agencies are always looking for public support because that's how they get their funding. And, you can also say that they treat safety as a major concern as well. And there's sort of the what I call the space enthusiasts. They want to see frequent progress towards the expansion of humans into the solar system. These are obviously somewhat in conflict, and you have to be able to address them. But once we have people up there, it is very doubtful that we're going to say, "Hey, guys, we're not going to take care of you." So, but that's one future. They could say, "Well, we're going to just come home. That's all." That's part of an uncertain future. Could happen.
All right, look, many of the questions that you are asking actually are going to be addressed by other international experts next week. We have in Sydney, we're hosting the Off-Earth Mining Forum. It's at the Technology Park. I guess, when I was sitting there, I was realising, well, this is probably the first event that's related to that. We've got a number of public speeches as well as the forum itself. And so questions of economics, questions of law, questions of ethics were all asked. We have speakers on all those topics. So please look that up if you've got a genuine interest in this area, because the opportunity to listen to experts like this in Australia doesn't come along very often. So, I guess it's just to thank Bob for his contribution tonight. Thanks very much, Bob. You can hear Carlos next week, talking about his model.
On Thursday.
And Bob has another talk on Thursday at lunchtime on system engineering.